Ooh, all right. And we'll get the drawing tools up. Okay. So we're going to finish the top end on our engines tonight. And the first thing we have to do that is get the heads on. And so we have actually talked about resurfacing in the past, and you guys have gone through the A class where you focus on heads. And I just can't stress enough that when it comes to getting your heads to seal up, it's all about having everything nice and flat, right? So it's all about flatness on there. Using good fasteners, right? Whether they're torque to yield and they're one-time use, or you can, sometimes with torque to yield, you can use them a certain amount of times if you measure the fasteners, depending on what the specs are. But good fasteners, proper torque procedures. So fairly recently, my son and I were working on his Ford Thunderbird, and these were the heads on that thing. And it was and here's the torque procedure. It was a 5-step torque down. Now this is the Ford Thunderbird Super Coupe, or SC. And so it's a 3.8 liter V6 with a supercharger on there and aluminum heads that were specific to that engine. And these things were kind of notorious for blowing head gaskets. And I raced with some folks that they were trying to lemons race one, and they were constantly blowing head gaskets. I seriously doubt that they were making sure that stuff was flat, and they were following the procedure here to the letter. Also, with something like this application, MLS gasket probably would help for what you're trying to do. But you can see that you basically evenly torqued it down, then you backed it off right here. Then you had to back it off and then re-torque it down and follow the degrees on there. I mean, it was pretty intense. And honestly, I couldn't use this old style of degree wheel. There just wasn't enough room to work inside the car. And so one thing I would recommend, guys, is if you are looking at a torque wrench, it would be worth your time to save your money and get the torque wrench that can do the degrees on there. A lot of the manufacturers will call that style of torque wrench a like a tech angle torque wrench, something like that. And if you can get anything that gives you some angles, it's super nice, because it was hard to get on some of those head bolts. It was hard to get a full, these torque wrenches that have the inclinometer in them can you can go 10 degrees at a time. So anyways, flat surfaces, good fasteners, proper torque procedure is your keys to getting everything to seal up properly. All right, so with that, I got a quick video clip here for you, and we'll see how the CDX guys put the head gaskets on.
Clean the block deck surface and the decks of the heads with some lacquer thinner. Retrieve all of the head bolts from their storage bin to be prepared. If the head bolts go into holes that have solid bottoms to them, you only need to put engine oil on the threads and on the undersides of the heads of the bolts themselves. If any of the head bolts go into holes, then sealer onto the threads of the bolts to keep the coolant from leaking past the threads. They will also need some oil or assembly lubricant on the underside of the bolt heads. Look for any "this side up" or "front" labels on the head gaskets. If there are no labels, it shouldn't matter which side goes up. Just double check that for every hole in the block or heads, there's a corresponding hole in the gasket. Composition gaskets don't need any sealant on either side, but a metal shim gasket needs an even coat of high-tack gasket sealer sprayed on both sides. Gently.
So I guess I will say that one of the things I like about this clip is they show you all the prep work involved, right? Like it's got the locating dowels on the engine block. They've prepped the bolts that go straight into the water jackets, have the sealer on there, and they still have lubricant underneath the head of the bolt. They talked about prepping the gaskets and which ones you prep and which ones you don't. They do a good job with that. And it's all those little details that oftentimes get overlooked, and that's why people have failures. Oops. Well, let's see here.
Clean.
I'm going to have to switch something for you here because I accidentally reset my video, which I didn't want to do. And so what we're going to do is look at it this other way. How much? Install heads. And
Clean the block deck surface and the decks of the heads with some lacquer thinner. Retrieve all of the head bolts from their storage bin to be prepared. If the head bolts go into holes that have solid bottoms to them,
I'm going to fast forward this to where we were.
It's a little nice organization there.
Yeah, you know, so let me look at this right here, right? I've worked with guys, and actually some of my teachers, you know, they'll have students put stuff in plastic bags, but honestly, if you're doing a lot of engine work, you usually have a series of like plastic organizer trays for your common stuff. My one complaint is that some of the bolts inside this divider looked a little rusty to me, but if you're doing stuff over and over, it's worth the investment in various plastic trays, because the bags honestly just make a big, huge mess, and they get oily and nasty, and so
Can't label anything either.
yeah, exactly. All right, let's get this thing going.
gently lay the head on the alignment dowels of the block and start threading in the bolts. If you have a few different sizes of head bolts, make sure that the right bolts go in the right places. Also, install the safety pin in the stand to keep the weight of one head from spinning the engine upside down before it's balanced with the other head. Go through each bolt on both heads and make them hand tight with a wrench. Torque in 3 increments, resetting the wrench and increasing by 1/3 each time. Cylinder heads require that you torque the bolts in a certain sequence. Most heads have a similar sequence to this engine. Start from somewhere in the center and tighten in a spiral pattern towards the outer bolts. If your engine has its own particular pattern, follow the instructions in the repair manual. Sometimes it's hard to keep track of which bolts you have torqued and which you haven't. Make a note of how many total bolts you have and count as you go. When you get to what you know is the last bolt in the sequence, but your count is one short, then you'll know that you missed one. You should double check regardless, especially when you get to the final torque specification.
I really like how they did that, how they showed it's a circle and you're working your way out. A lot of times I'll relate it to, like, if you're putting a bumper sticker or something on your car, you're laying down some graphics and you don't want to get air bubbles in there. You start at the center and you force those bubbles out, right? So that's your normal torque procedure. And then on disassembly, I'm one for where I'll start from the outside on disassembly and bring my way in. So I really like how they graphicked that out for us. Did a pretty good job with that. All right, I'm gonna go ahead and go back to the slideshow. And there we go. And we'll move ourselves over. Minimize that. All right. So at this point, now we got the short block was built last week. We just got the heads on. Next thing we're going to start doing is putting the valve train back together, right? And you know, on a lot of engines, like Phil, your Subaru engines, right? Your timing chain assembly can start being a little bit elaborate. But the big point that I wanted to get to, that I see a lot of my students get messed up on, is they get all messed up on their valve adjustment when they go from you know, solid versus hydraulic lifters. And remember, it's two different things. Now, we were talking about an organizer tray here a minute ago. Here's one that's specifically set up for.
That's kind of like Chris's, but just for valve trays.
Yeah, and it works. It works pretty good. You know, for organizing up all your valve train, right? So you can keep all the rocker arms in order, all the valve springs, all the push rods, all the lifters. The biggest thing is the cam and lifter set is critical. And you're going to hear me, I'm sure I beat you up about it before, but you'll hear it again tonight. If this is my cam lobe and this is my my lifter, remember that the lifter's offset a little bit. On a solid lifter, this thing's designed to spin, and these two guys get wear mated to each other on that first few minutes of startup and break-in. And if I start switching lifters, I can quickly wear out a cam lobe. So you absolutely have to keep the lifters in their order. Otherwise, if you throw them in the wrong order, you're going to wipe out your cam. So I say, if in doubt, just replace all the lifters. The other thing I would say, if you're doing an engine build on a flat tappet cam, you're probably, and it's a high mileage build, you're probably going to be putting a new camshaft in there anyways. That's just one of the things you normally change. So valve adjustment, of course, if I have solid solid lifters, right? Solid stuff, I'm going to have a little bit of lash on there, a little bit of clearance. But if I have hydraulic lifters, well, with those guys, I'm going to be setting them to a certain amount of preload. So it really depends on what I have inside the valve train there and how it all goes together. So I can't stress enough the importance of, you know, looking at your procedures and double checking stuff on there to make sure you're doing it right and setting it up right. All right, so this video clip's going to go over the hydraulic one, which I think a lot of people, they seem to struggle more with hydraulic than they seem to struggle more with hydraulic than with setting solid where you have lash. Remember that when you have a hydraulic lifter, right, you have this inner plunger that's fitting inside the outer plunger. And basically what you're trying to do is get a little preload on there so that if the clearance gets bigger, it can expand and take up that preload. But if the clearance gets smaller, you can also, this thing also still has room to take that away as well. So you're basically setting the inner plunger of the lifter in the right spot. A great way to do these, probably arguably the best way to adjust your valves on hydraulic lifters is to do a running valve adjustment.
So with the heads off.
Well, so you have your heads on, but what you have to do is take your valve covers off, or and so, you know, obviously this is only going to work on certain engines. But let's say you have a classic, you know, Chevy or Ford or something. A running valve adjustment, you know, you take an old set of valve covers, or they sell little clips you can put on the rocker arms, and you can adjust it running, where you loosen it up until it makes a clatter noise. You tighten it up just till the clatter goes away, and then you do your additional half turn or one turn, whatever you need to set this preload. So, but you have to have, you know, you have to have your stuff set up to do that running adjustment. Honestly, if you have a new set of lifters on a normal engine, you don't have to do that. Some, like if you're working on an old Corvair or a Porsche that happens to have hydraulic lifters, something where it's air cooled, it's got a wide temperature range, so there's a lot of growth and shrinkage in it. The running valve adjustment works good for that. A lot of stuff is just not quite necessary unless you're really fighting an adjustment. All right, let's check it out. Clear my drawings. There we go.
If the engine has rocker studs or pushrod guide plates, put them on now. Then put your valve train organizer tray near the engine. In almost every rebuild, the camshaft is replaced, and so are the lifters. If so, the new lifters can go in any order into the block. The bottoms of the lifters that ride on the camshaft should have the same type of lubrication as the cam lobes. The sides just need oil or assembly lube, and the lifters can slide in. If you are reusing lifters from the organizer tray, they have to match back to the exact same cam lobes or they'll wear out much more quickly once the engine is running again. The same goes for the push rods. The same end has to be facing up to keep them from having problems later on. Before the rocker arms go back on, lubricate the cups of the lifter plungers where the push rods sit, and lube the tips of the push rods and the tips of the valves, so that when the rocker arm comes out of the tray, there will be no bare metal rubbing on metal. Lubricate the rocker pivot balls too before you put them in. Tighten the rocker nuts only finger tight for now.
All right, so now we'll adjust them. We got everything together. It's all in the same order. Ideally, we used a tray just like they had there. They're not very expensive. Now we're going to adjust it up.
Just as you did for the pre-assembly check, for the final assembly of engines with hydraulic lifters, you need to adjust to 0 lash so that all the slack is taken out. Then tighten the nuts down another half turn. When the lifters are installed, every time the engine rotates, the protective lubricant is being slowly wiped off the cam lobes. However, if you follow the firing order of the engine, the camshaft only has to rotate 1 full turn to carry out the whole lash adjusting procedure. As you rotate, look at the intake lifter or pushrod of the number 1 cylinder. The exhaust will open first, and then the intake. As soon as the intake returns to lowered position, stop rotating. The cylinder is now on its compression stroke, and both lifters will be in their lowered positions. If you have non-adjustable rockers, you can install both rocker nuts and tighten and torque them for the number 1 cylinder. For adjustable type rockers, spin the pushrod with your fingers as you tighten the rocker nut. It can be difficult to tell the exact point where all the slack is gone and the pushrod becomes a little harder to spin. While you're turning, feel for a slight difference in resistance to spinning the pushrod. That should be the 0 lash point, where the pushrod is unable to move up and down at all. When you get close to 0 lash, it helps to hold the wrench up a little bit so that the socket is not sitting on top of the pivot ball. When you are sure the valve assembly is at 0 lash, align the wrench straight and give the nut exactly 1 more half turn. This pinches the plunger down on the hydraulic lifter to set the preload. When the engine is running and oil fills up inside the lifters, the preload on the lifter keeps the valve train from making chattering noises. When you add the extra half turn to a reused hydraulic lifter that already has oil in it, the valve may actually open slightly. This is normal. If you had a gauge installed, you would see that after a minute or two, the pressure inside the lifter will bleed off and the valve will return to its closed position where it should be. The firing order will tell you which rocker to adjust next. On a V8 engine, whichever cylinder is the next after the first will already have the intake lifter in the up position. Rotate the engine about a quarter turn and the intake lifter will return to its bottom position. Then adjust the rockers for that cylinder. Carry on through the firing order, and each time, the next cylinder will have the intake lifter in the up position. When all of your rockers are adjusted, the camshaft will only have rotated once, and there should be plenty of break-in lubrication left on the cam lobes.
Okay, so
Seems
they
simple.
were really hitting us up about, try not to wipe all that lube off the cam lobe. And I got the guy muted here, and I'll just play it to get a little bit of a picture going. Remember, a flat tappet cam, there's a lot of pressure there. So there was a couple things that I really liked here. One, they have you minimize rotating the engine over and over and over again to keep the high pressure assembly lube on the lobes of the cam, which was really good. The other thing is that they're doing the valve adjustment on this fresh engine build. They haven't put the intake manifold on. And I think that's a great way to do it, because with the intake manifold off of the engine, you can see what the camshaft is doing essentially by looking at the lifters, right? You know, if the lifters are down, I can adjust those. And so like I can adjust both of these. I could actually adjust this one right now. I can adjust that one. But I couldn't do this one because he's being pushed up. So is that guy right there, right? These look like they're down. So it really makes adjusting the lifters and setting that, doing the valve adjustment, adjusting the lifter preload really makes it quite easy to do when you can see what's going on inside the engine. I find that if I have a group and they put the intake manifold on, you know, they 9 times out of 10 get it all messed up and, you know, end up where the engine doesn't want to start because multiple cylinders do not have compression because they've over tightened these valves. While we have this image up, remember on this engine, the small block Chevrolet, these rocker studs are just pressed into the heads. And in the heads class, you guys probably talked about how some guys might want to pin these. Yeah. Maybe some of your classmates machine this down and put a thread-in rocker stud in the engine, so that's a little bit more secure. But essentially, this is your valve adjustment right there. If I had replaced these with solid lifters, I would be taking a feeler gauge and actually setting a certain amount of lash or clearance right here because of that. And the last thing I want to say related to lash is usually when I'm building a new engine, especially if it's something that's got a pretty healthy cam in there, I'm going to set it up to 0 lash so there's no preload, and get the engine fired up, get the lifters all pumped up, and then I'll take the valve covers back off, assuming it's easy to do so, and then I'll put in my then I'll put in my preload. And that preload might be, you know, it might be a half a turn, it might be one turn, whatever the spec is. So that's how I like to do it, and it works pretty good, especially if you got maybe a lifter set that is a little shaky or something. All right, so now we got the valve train in. We've already, you know, the timing chain's on already. The heads are torqued down. So now it's the intake manifold goes on. Intake manifold installation is pretty straightforward, but there is a couple things that you'll see on some manifold designs. I got a little video clip for you that's going to go over kind of this style of intake manifold and what products and stuff to use. Keep in mind that this is a pretty large surface area. So again, there's a torque pattern that typically is going to start in the center and work its way out just like we saw before, right? We have to be especially careful on a lot of our new plastic composite manifolds because those are known to crack and have issues. On engine disassembly, I always check these out really good because oftentimes you go to take it apart and it's cracked, right?
Do those bolts?
I also have V engine fitment problems up here on the screen. Remember that if this is my engine block and I've now shaved down the heads on, or the deck surface, and maybe I've even shaved down the heads. Now my head's not looking real good there. Well, now I might have where I go to put my manifold on and the bolt holes don't line up how they're supposed to because of the milling, and I might have to shave material from the manifold. So those are all things that you have to think about, especially if a lot of machine work has been done, that the manifold may not line up correctly. Again, the correct sealants and the torque stages are pretty important. There's one thing on this video clip I don't like, but it is realistically what most people do on this style of manifold right here. So we'll go ahead and jump into it. I think.
Start with a solvent cleaner, such as lacquer thinner. For most engines, it's a good idea to put some silicone sealant on the four corners where the heads meet the block. Put some gasket sealer around the water jacket ports and their mating surfaces on the intake gaskets. When the sealer on the gaskets is tacky, line up the bolt holes and stick them into place. Then spread some more gasket sealer on the tops of the gaskets around the water jacket ports. On any engine, if the decks of the heads or the block or both were machined, the heads will sit a little bit lower and the gap between the engine manifold and the block rail will be smaller. Some gasket sets have rubber or cork gaskets that will be too thick to allow the intake to seat properly. These are not recommended. Instead, to seal the block rail to the intake, run a solid bead of silicone sealer along the front and rear upper rails of the block. Run the bead evenly from gasket to gasket. This is a good idea for all engines, whether the decks have been machined or not, because it provides a much better seal. When the block is ready, double check that the oil splash guard is in place on the bottom of the intake, if it has one, and then lower the intake manifold into place. Get some help if you need it. Cast iron manifolds are very heavy, and it is important to lower it as close to its final position as you can. The aim is to need very little adjustment to get the bolt holes to line up. On most engines, the intake manifold bolts lead directly into the oil-soaked area under the valve covers. Treat the threads of these bolts with non-hardening sealer to avoid oil leaks. It's sometimes hard to get to the bolts near the plenum of the intake with a socket. If that is the case, use the ring or box end of a wrench. The intake bolts usually have a tightening sequence similar to the heads, but the sequence usually starts with the middle bolts near the plenum. If you can't get to all the bolts with a torque wrench, tighten to the first torque increment one of the bolts you can get to. Then put a box end wrench on the same bolt and feel with your hand how tight it is. Now you can guesstimate how tight to make the first few bolts in the sequence. Do this for the first few inaccessible bolts for each of the 3 increments, and you should end up with all the bolts torqued to a similar rating.
So I would say that's not ideal, right? If you put a crow's foot on your torque wrench and you could use the calculator and figure out what the modified torque value is, that would be better. But what you saw in the video is what most people do. They just kind of, this is about what feels like by hand. I did like how they put the sealant on the bolts and they lowered it down. And I'll tell you, those cast iron manifolds are sure heavy. You can easily pull 100 pounds of weight off an old engine by going to aluminum heads and aluminum manifold. So with that, we'll keep going. So now we got our intake manifold on. I wanted just to throw this up. We actually, I had these slides up last week, but knowing the right product to use is important, right? And I said whether it's a valve cover, you know, the cylinder heads, right? Flatness is really important, using a torque wrench and the right. So sometimes, like if you're doing a gallery plug, you'd want a non-hardening sealer. They put that big thick bead of RTV on the valley, and that's actually what like Eldebrock and a lot of the manifold manufacturers will recommend. That works better than the rubber gaskets, and I've had better luck with it as well. Now, if you're doing a modern engine that doesn't use gaskets, you know, you're using a lot of the sealers on a lot of this very tight precision stuff. You don't use a very thick bead, but in that particular spot, like you saw in that video, between the valley and the manifold, there's usually a pretty decent gap, and so a thicker bead of silicone works well there. So use the right product for the application, and Permatex has these different charts to go up. Loctite, which I think Permatex bought them out a couple of years ago, but they have similar charts, so you can make sure the product you're using is right for the application. With that being said, usually, remember my rule is silver and black, and I got that from the Permatex guy that used to visit my class. You know, ultra, gray. If you use those two, ultra gray is very similar to most of the products that import manufacturers, whether it's Subaru or Toyota or Honda, will use. Ultra black is what you find being used, or a very similar product on most of your domestics. If you stuck with those two, you'd probably be in good shape, getting your stuff sealed up for anything that's requiring an RTV, which stands for room temperature vulcanizing sealant. Okay. All right, so then you got your finishing touches. And I made sure I put this slide in here because I see this part get all screwed up all the time, where you have a, overall a pretty good engine build. Like the machine work was done right, new pistons, ring gaps were set correctly, all those types of things. And then you get to that last 10% and do crappy work, and the whole thing looks bad. It's leaking oil or leaking coolant. Or I have a lot of problems with some of my ARC students not using this tool correctly. It drives me nuts. And then there's some stuff that, sometimes even I myself forget. Like I mentioned, my son and I were doing that supercharged Thunderbird. Well, we're trying to get it out of the college because they're locking it down, right? We want to take the car home. Yeah. And we go to put the manifolds on and stuff isn't lining up. And I've checked these guys. The manifolds were flat. They looked like they were in good shape. The bolt holes didn't line up, and we ended up getting all messed up because the access was really poor. Well, what happened was that even though stuff had lined up, the flatness was okay. The manifold was warped enough where, like, these logs here had moved just enough that now the bolt holes didn't line up correctly. And I ended up, because I didn't catch it ahead of time, otherwise I would have maybe got some new manifolds. I ended up having to drill out the holes in the manifold a little bit bigger so I could get everything to line up. But we were kind of scrambling around with that one. So, don't let that last 10% mess you up, right? Follow torque procedures, use the correct products, and have the right tool for the job, and that will go a long way. All right, and oops, I think I got one for this.
If the balancer has scratches on the sealing surface, fix it with a repair sleeve. Also, if this engine rebuild will not be completed for a while, you should coat the sealing surface and the inner diameter with a white lithium grease. Use regular grease if that's all you have.
So I wanted to just show at least the beginning part of this, because what they're using is what we'll commonly call in the industry as a speedy sleeve that can repair the balancer, and so you can use it again. Remember that, how did that seal wear a groove inside the balancer? Well, it probably had pretty poor oil changes in its life. And so then you get carbon in the oil, right? Byproducts of the combustion process. Carbon gets in the oil. Carbon is very hard. It gets impregnated in the seal. And then that's how the seal starts wearing out the steel balancer snout there. So I would actually recommend that on an engine build, hey, let's put a new balancer on there, because it's likely before that new engine's worn out that this balancer is going to slip. I'd rather put a new balancer on there and make sure that everything's spun up on the balancer machine in the machine shop before I gave it back to the customer. All right, so they're putting on the speedy sleeve. Let's see what else they're going to do.
Fit the balancer onto the nose of the crank and line it up with its keyway. For a press-on style balancer, don't simply hammer it onto the crank. Use a good quality harmonic balancer installing tool and thread it into the same threads as the center bolt of the crank. Draw up the installer nut and start turning. If it seems to bind up as it's going in, check it or pull it off and start again. If it starts to get crooked, you could end up snapping off the nose of the tool in the end of the crankshaft. When it gets close or is all the way in, the crank will start to spin. If it is not fully seated, install the flex plate and disable the rotation of the crank to press it on the last few millimeters. This is what can happen if you put too much pressure on a cheap tool. If you are not sure if the balancer is in all the way, you'll know for sure when you line up and install the pulleys and belts. Clean the fuel pump mounting surface. If you have one, lubricate the fuel pump push rod and slide it into the block. Be aware that if you let go of it, it will slide out again. If you have a cover plate, gasket sealer goes on both sides of the plate gasket. Then the plate goes on with its holding bolts. More gasket sealer goes on both sides of the fuel pump gasket and some on its mounting point on the block. For most engines, when the balancer is set to top dead center for the number 1 cylinder, it's easier to install the fuel pump. Make sure if you have a push rod that it is up inside the block, then install the bolts and torque them to specification. On the front of the engine where the water pump fits, put plenty of gasket sealer on the metal and gasket surfaces.
All right, we'll go ahead and pause it right there. The rest of the stuff's pretty straightforward. I can't tell you how many times I see students, you know, a lot of your American cars have these pressed on or interference fit balancers, right? Where import cars, they normally slip on and off. I can't tell you how many students I've had just try to like put the bolt in the center of the balancer and impact it on. I have a bunch of crankshafts that have their threads torn out from people doing that. So I really wanted to at least demo that tool. Keep in mind, if you're working on a Chevy, Ford, or Dodge, it's very likely that you're going to have to use a puller to remove the balancer and an installer to install it, just like we saw here. Again, don't get to that final 10% and let your quality go in the toilet. All right, so now we're pretty much there. We really, before I put the distributor in, I would pre-lube it. I have that in my other presentation. I do want to get over timing, and so we're fitting that in right now. Timing the engine, I mean, this is an absolute classic shop test. When I started working in the industry, it was kind of like if they wanted to test to see how smart you were, they'd be like, well, you know, try to get that engine running, the distributors out of it, right? So it is still a classic test, especially if you happen to be working in an older shop where they have cars with distributors. I still think it's relevant because it really tests your ability to understand what's going on in the 4-stroke cycle at the right time. And quite frankly, I see lots of engines, you know, like at a car show or something, and I can look at it and see, well, that person stabbed the distributor on. It might be running, but they really didn't stab it correctly. So like in this picture here, they have this small block Chevy here. You can see that the vacuum advance is facing that side, and number 1 cylinder should be, or the rotor tip, if I'm at top dead center compression, should be pointing basically towards number 1 cylinder in the engine. Yeah, I mean, if the rotor was pointing over here, I could you know, reroute my spark plug wires and route the wires so that this was 1, and then start moving everything over in the firing order. So make that 1, make that 8, but that's just kind of a sloppy job, right? So you have to find top dead center, and specifically top dead center of the compression stroke. If you're smart, you can preset your timing advance down on your harmonic balancer by, like, let's say your timing spec is 8 degrees before top dead center. I'll go ahead and advance that thing to 8 degrees before top dead center and then drop my distributor in. I mentioned this. The other thing that makes this a little tricky is you're trying to get the oil pump drive to engage. So sometimes you have to get in there and move that a little bit. But, you know, I do still think it's a good test because it tests your understanding of what's going on inside the engine and how the 4-stroke cycle comes together. That being said, if you don't have a distributor, right, cam and crank sensor, right, do they have the right gap on them? Is that the right camshaft sensor? Do you have the right reluctor wheel on there? I've seen cars where they rebuild the engine, it won't start, they're cranking it, and they somehow in the build process, they ended up pulling the reluctor ring off the crankshaft or all kinds of crazy things have happened, and now the car won't start properly. Some engines you have to do a relearn process for the cam and crank sensors, so the computer knows where everything's at in the 4-stroke cycle. So with that, one last video clip here.
Lower the distributor into the distributor hole. Look at the distributor and you'll see that the rotor is connected to the distributor shaft. The distributor gear is also connected to that shaft. The gear in the distributor and the gear in the camshaft are both helical gears. When the distributor slides in place and the teeth of the distributor gear mesh with the camshaft gear, the rotor will move slightly as the helical gear teeth interlock. The slot in the distributor gear has to engage the slot in the oil pump drive shaft, which is already fitted onto the oil pump. Often this won't happen on the first try, which will mean the distributor may not seat all the way down flush with the block. This is because the oil pump drive rod may not be in the right position to perfectly line up with the bottom of the distributor gear. During pre-assembly, it was possible to rotate the oil pump drive rod by hand and the distributor dropped all the way down. Now, with the oil pan installed, the oil pump drive shaft has to be rotated by hand from the top. The ideal tool to use is the oil pump primer rod. Put it into the distributor hole and rotate the oil pump drive rod a very small amount. Then give the distributor another try. If it won't drop down yet, rotate it with the drive rod a little more and then try the distributor again. Make sure you hold the body of the distributor in the same position each time. Eventually, the distributor gear will engage the cam gear. It will rotate slightly as it interlocks with the cam gear and slip right into place once it lines up with the oil pump drive shaft.
So on an engine like this small block Chevrolet, to prime the lubrication system, you do need one of those tools, or you need a distributor that you've taken the guts out of that can spin the oil pump. You know you have it set down there properly when it fits all the way down and touches the base of the intake manifold. I see a lot of times people fight this. They're not engaging the oil pump drive, or that when they get it engaged, because of the angle of the gear, now the rotor's pointing the wrong direction. You know, this is something that every semester I have students really struggle with this. And I saw, you know, guys in the shop struggle with it. If you do all this correctly, you can get the engine what we call static timed, right? The distributor's stabbed. You've preset the timing, the specified amount of advance. The spark plug wires are on, and that thing will fire up. And then when you go to shoot the timing with your timing light, it's going to be almost right on the money right away, which is what you want. You don't want to have to crank and crank and crank and crank your engine because the whole time you're wiping lube off the camshaft and everything else. All right.
Now the distributor should be fully seated flush with the block or intake manifold. When installing the distributor, the goal is to get the distributor into place and have the rotor that's bolted to the shaft pointing in the general direction of the number 1 piston. This is not a firm rule, more of a general guideline. If the rotor tip is pointing in some other direction, the distributor is still installed correctly, but you will need to make a mental note of where the distributor is pointing. Before you install the spark plug wires, the engine must be set to the initial timing setting recommended by the manufacturer. This setting should be listed in the repair manual, but in some cars it can be found under the hood on a sticker or label in the air cleaner or radiator. If you don't know what your initial timing setting should be, a starting point of 10 degrees before top dead center will be good enough for the break-in procedure for your engine. Use this simple method to set the engine to an appropriate initial setting of 10 degrees. If you have a top dead center whistle, screw it into the number 1 spark plug hole. Alternatively, plug the number 1 spark plug hole with your thumb and rotate the engine by hand. If the timing mark passes by and you don't feel or hear air coming out, that means you just passed the exhaust stroke, and you need to keep rotating. When you feel air rushing past your thumb or hear it through the whistle, take a look at the timing mark on the balancer. Move the crank very slowly, and when the timing marks on the balancer and timing cover line up and read 10 degrees, or whatever your initial timing is supposed to be, stop turning. Now the engine is paused at the exact moment when it will fire a spark from the distributor to the number 1 spark plug. Remember, the top dead center mark on the crank will go around twice for one rotation of the camshaft. If you didn't feel or hear the air rushing out of the spark plug hole before the mark lined up, you might have your mark set for the initial timing of the exhaust stroke. Make sure you felt the rush of air, then set the crank at the initial timing setting.
So I have a lot of problems where people, for whatever reason, they don't have tuned up thumbs. They can't feel the air. So another thing you could do is just take the valve cover off. An engine like this, it's pretty easy to do that. It's 4 bolts. Take the valve cover off and look at the rocker arms, right? If neither valve is being opened, you know you're at top dead center, right, on the compression stroke, because you're either going to be top dead center compression or top dead center exhaust, right? And so if the exhaust valve is being pushed open, right, you'll see the rocker arm moved, and it's pretty obvious. So oftentimes I've thrown away them to being able to feel if it's building compression or not, and I've just gone by look at the valves. Okay, neither valve's being opened. You're on the compression stroke, and then line up the marks to where you're at top dead center.
The distributor cap will only fit on the distributor one way, and when it's on, the body of the distributor can still move left or right to make the spark happen sooner or later as the engine is running. As the engine is at the point of ignition for the number 1 plug, one of the cap towers must line up with the rotor tip. With the cap off, hold something as a pointer against the engine and point it directly at the rotor tip. Lower the cap in place and then line up one of the spark towers of the cap with the pointer by rotating it left or right. Whichever tower has the rotor lined up with it now needs a label. This tower will hold the number 1 spark plug wire and will be the starting point of the firing order sequence. From here on, don't let the distributor move. Tighten the hold down clamp so that the distributor body is locked into place, and then tighten down the cap. Install the spark plugs. Check the engine specifications for the plug gap rating and heat range. The gap is directly related to the ignition type, fuel octane, and compression ratio. There are a lot of different plug gaps, so make sure that you find the right one for your engine. Don't forget to use a small amount of anti-seize lubricant on the threads and torque them to whatever the engine specs say. The crank is now positioned, and the distributor rotor is parked at the moment of ignition for the number 1 cylinder. Every firing order for every engine type starts with the number 1, and then the rest of the numbers in the sequence will follow the valve opening events built into the cams of the camshaft. The engine must match this sequence or it will not run. There may be a diagram in your repair manual, but to correctly wire any distributor, all you need is 3 pieces of information. You need to know the cylinder numbering, the direction the distributor rotates, and the engine's firing order. We already have the rotor inside the distributor set. The firing order, as you read it from left to right, needs to happen in the same direction of rotation that your distributor turns. For example, on a lot of engines, including this one, the firing order starts with 1, 8, 4, 3, and the distributor rotates clockwise. On some other engine, the firing order could start with 1, 3, 7, 2, and the distributor might rotate counterclockwise. The specifications in the repair manual tell you which way to wire up your distributor. Distributor tower 1 is at the moment of spark for the number 1 cylinder, so connect the wire from the tower with the mark on it to the number 1 spark plug. Every time the rotor hits that point, the spark will go to the number 1 cylinder. This distributor rotates clockwise, and the next number in the firing order is 8. So, connect the next tower in a clockwise direction to the number 8 spark plug. Continue on following the specific firing order. Try to judge the lengths of the wires as you go, so that you don't have too much or not enough slack when you get to the last couple of connections. This type of distributor has an ignition coil built right into the cap. Some engines have separate ignition coils, and their caps will have a short wire that comes out the corner of the cap and into the coil that'll be mounted somewhere nearby. When all the plug wires are connected, double-check the order of the wires. All
right, so it makes you realize how nice it is to have coil over plug ignition or even DIS, because you got a lot less plug wires and stuff to route. One of the things that I want to point out that I don't know how I made it out of school without knowing this, but I remember it kicked my butt the first time. Being more of a Chevy person, if you looked at some of the graphics, how they did this engine, right? You had cylinder 1, and then this is 3, this is 5, and that's 7, and of course it went 2, 4, 6, 8. So you had an odd bank and an even bank, right? Well, that's not how Ford does it, right? If you're Ford, the blue oval guys, I'm not supposed to say Ford. This is a Ford. Ford goes 1, 2, 3, 4 on this side, 5, 6, 7, 8. So just like it said, you have to know the cylinder arrangement. You have to know what the firing order is and what direction that distributor is rotating. And really, if you have those 3 things all put, you know those 3 things, you should be able to set this up and time it and get it to fire up. And you'll be surprised if you do it just like you've seen here, your timing will pretty much be right on the money. It'll be right there. So, all right. So with that, our engine is assembled. I got one little short presentation for you left. That'll be about pre-lube and break-in. Okay, how are we doing?
Hanging in then.
All right. So what I'm going to do here is I'm going to share this one, and we'll close that out, and we will put that up. Get that going right there. All right. Very good. All right. So most important 20 minutes of your engine's life is how you're going to break it in, right? That first fire up. And it's kind of a scary situation because the thing starts smoking and it's making noise and you're trying to get the air purged out of the cooling system. It can be a pretty stressful situation. Obviously, making sure like the ignition timing is working right off the bat is a good way to go. But before we get to the break-in, it's important to talk about the lubrication system because these 2 things are closely related. So we're going to do a few slides on your lubrication as we get there. This engine in the picture here, this thing is one of those Chrysler 2.5 liters, like you used to have a LeBarons and stuff, and they were turbocharged. So for their day, that was a pretty high-tech engine. All right. So remember that your lubrication system, it has pressurized lubrication, there's splash lubrication on there, and that most everything will have a full flow oil filter that's going to handle the majority of that, or handle all that oil flow as the pump moves the oil through the engine. Also keep in mind that the basic purpose of lubrication is to keep these moving parts from touching each other, right? Keep moving parts from touching, but a lot of other things happen as well in that the oil also helps cool the engine. In fact, somewhere on the range of 20% of your engine's cooling capability actually happens through the oil. Now, if it's an air-cooled engine, that number is even higher. Rotary engines require, put more strain on the lubrication system to provide that cooling. So it doesn't just, keep the friction down by keeping parts from touching. It also does quite a bit of cooling in the engine, and of course, the detergents in the oil help try to keep stuff clean and everything else. All right. Just like we saw in the previous videos and stuff, on a conventional engine, right, an old school engine, if you will, traditionally the oil pump was driven by the distributor, which of course was then driven by the camshaft, right? So you had multiple pieces going in there. So if I was shearing distributor drive gears and stuff, one thing I would be looking at is the oil pump. There's a couple other notes on this as well. If you, let's say you put some billet high performance steel camshaft in there, you better have a brass gear on your distributor. You don't want 2 of the same type of metal rubbing against each other. So there's some precautions when you start to modify things. Modern engines will typically drive the oil pump directly off of the crankshaft, right? So their gearing and stuff is going to be a little bit different for that. Okay, different types of oil pumps. There's gear pumps, there's rotor pumps, like is in the image right here. There's also vane style pumps, and now a lot of modern engines have variable displacement oil pumps, so they can change the displacement of oil based on how much oil the engine needs, right? So it's going to increase the displacement at low RPM, so it's moving enough oil through the engine. When you're going maybe 2,000 RPM, 3,000 RPM down the road, it might pinch off the oil flow a little bit to reduce pumping losses of the oil through the motor. All right, let's check out how that oil pump works.
A normal pump is capable of delivering more oil than an engine needs. It's a safety measure to ensure the engine is never starved for oil. As the pump rotates and engine speed increases, the volume of oil delivered also increases. The fixed clearances between the moving parts of the engine prevent oil from escaping back to the sump, and pressure builds in the system. An oil pressure relief valve stops excess pressure from developing. It's like a controlled leak, releasing just enough oil back to the sump to regulate the pressure of the whole system.
So again, the reason a modern engine, like let's say you buy a Chevrolet Volt, that thing's got a variable displacement oil pump, because any of this oil that you're just directing back to the pan, hey, that's horsepower loss, right? So they're trying to minimize how much oil just gets dumped back to the pan. If you're using a high volume oil pump and you're using the same pressure inside there, you're just going to be pumping more oil back to the pan. A lot of times that high volume pump will also include a different spring in here so that you end up with more oil pressure in the engine. All right. So I have here, hey, the oil pump, it can be the garbage pit of the engine, because all the junk goes to the bottom of the pan. And remember, before it goes through the oil filter, it goes into this oil pump. And so the only thing it has is this little filter screen here to try to filter out the big chunks, right? So a dirty engine typically will start wiping out oil pumps. If you're doing an engine rebuild, you know, pretty much bank on that you're going to be putting a new oil pump in there if it's something that's had a lot of contamination or it's got a lot of miles on it. Again, like I said before, if you experience distributor drive problems, check the oil pump. And I say that because we had a customer where he had his engine worked on, and I don't know what they screwed up the oil pump, and they, you know, the car would go, I don't know, 2,000-3,000 miles, sometimes 5,000 miles, burn up a distributor, and they kept just throwing distributors in it. And it all came down to the oil pump, right? So I made the note on the variable displacement. So everything's got to be, you know, way overcomplicated on modern engines. So I get how it makes it more efficient. My concern with that variable displacement pump is now you have one more thing that can fail, and fail in a big way. Okay, so if I'm doing some oil pump checks, if I'm going to reuse the pump, there's going to be a whole series of clearances that I need to check with the straight edge and a feeler gauge to make sure that I can reuse these pieces, right? Pressure relief valve spring, right? That's how I'm going to control what the maximum oil pressure is on top of what my bearing clearances and stuff are, right? Ultimately, remember, if you're fighting low oil pressure, well, did you get all your bearing clearances correct, right? So there's going to be specs on that. If it's a older style engine, something where you have a more of a replaceable pump and not an integral pump, like this one's kind of integral with a case. If you have something like that, something like this image here, I would just replace the oil pump. Modern stuff, you're likely going to have to check it because you won't be able to replace the whole pump. It'll have some type of integral housing to the engine case or something like that. So clearance checks become a big deal. Here's a few shots of just worn oil pump components. This was off of a Ford engine. You can see the different drive, and you can see this one's all bent up. There was the oil pump had sucked in so much junk. You can see the wear on the cover, and then it twisted the drive shaft and ended up messing up the distributor drive shaft. So, all right, a little bit of oil filter tech. Remember, it's not just a filter. Oftentimes your spin-on filters, they have an anti-drain back valve to try to keep the oil in the filter. They also have not only the filtering media there, right? And of course, the better the filter, the more pleats of paper you're going to have in there, so you have more filtration area. In the bottom of this thing, that there's a bypass valve that comes into play. We'll look at that in just a minute. There's that anti-drain valve. That's why it's hard to drain all the oil out of the filter. And of course, a good oil filter is going to have a better, thicker sheet metal case on there if it's a spin-on style filter. Now, one thing that I do like to do on a build, or if it's a race motor or something, is cut the filter apart like you see here. Take the filter apart, look inside there. It's a great way to see what's going on inside that engine, to see if there's any potential problems, if you see a bunch of metal shavings and stuff in there. If you've done a good job with your machine work and you've done a clean assembly and your clearances are right, even on a fresh rebuild, you shouldn't see a whole bunch of metal shavings inside that oil filter. All right. Oops. So with this, I have a little animation here. It just kind of shows the overall lubrication system. And I really like this graphic because, again, it shows you the main oil galleries. It shows you how we pick up the oil from the pan, send it to the oil pump. This pump here is driven off the end of the crankshaft. It will show us some stuff on the pressure control, right? So in these slides here, this would be low speed. The pressure relief is closed. Here we have the relief valve regulating, and here we're at higher engine speeds, and it's just dumping that oil back to the oil pan there. Notice that all the oil goes through the filter and goes to the main oil galleries. Now here we're looking at the filter, and you can see that the oil goes from the outside of the filter through the filtering media down into the center and out. That's the normal flow. However, if the oil filter is to get blocked, right? Let's say that filtering media on the sides is all clogged up. Well, then that bypass valve will open up with the idea that, you know, dirty oil is better than no oil at all. So if the oil filter gets really plugged up, usually takes about an 8 psi pressure drop through the filter, but that will cause the that pressure relief valve to open up, and it will bypass the oil filter. Okay, so we've assembled our engine. We're going to fill it with oil. What oil to use? You'll hear different things. You'll hear people say use multi-viscosity, but the traditional thing is people would say, hey, don't use a single viscosity non-detergent oil. The idea is that detergents in the oil could be harmful to some of the coatings on the bearing surfaces. I haven't seen that happen in modern oils, but being as that you're going to change that break-in oil pretty quickly, a detergent isn't necessarily needed. If you are breaking in an engine, especially if it's an engine that has a flat tappet cam, you're going to need an oil that has a fair amount of ZDDP additive or zinc, okay? This is your extreme pressure lubricant. So where we have that lifter and cam coming together with extreme pressures, you really need it. Now, this ZDDP, there's not a lot of that in modern oils. Well, why is that? Why wouldn't we put it in there if it's such a good extreme pressure lubricant? Well, it kills your catalytic converters. It kills the cats. And now that you have to, you know, a manufacturer might have to warranty a catalytic converter for 100,000 miles, right? They don't want to be damaging that cat any more than they have to. So part of the reason we've seen oil change intervals go up, not only because we have better oil, arguably better crankcase ventilation and stuff, is that every time you put in the fresh oil is going to have in it some of this zinc, some of the ZDDP. The zinc kills the catalytic converters. Well, we burn off some of that zinc on a fresh oil change. So every oil change kind of slowly poisons the cat a little bit. You want that cat to last longer. Pull the zinc out of the oil as much as you can, and don't change the oil so often. So that's kind of the modern strategy. So if you have an older oil engine, right, flat tappet cam engine, we're seeing more camshaft failures on those because there's less zinc in the oil. Obviously, if it's something high performance with stiff valve springs and stuff, lots of lifter pressure, again, a high zinc content oil, a race motor, something like that. So for stuff like that, what I would recommend is some type of zinc additive or a break-in oil, right? So here's a product made by Comp Cams. So you might use a break-in oil additive or a break-in oil. What you'll find with these types of oils, they argue that they have a quicker, more efficient ring seal. They give you the camshaft protection you want because they have more zinc inside there. They're set up usually with a minimal amount of detergents in there. And the idea is that you can drive and race on these things. They're pretty good oils, but they do a better job protecting the camshaft and braking in the engine. And in theory, they're going to promote a quicker break-in period than a conventional oil. And if I had spent a lot of money doing an engine rebuild, I think it would be cheap insurance to put some good break-in oil in there. Now, when we're breaking in our engine, remember the two big things that we're breaking in really are the rings, the pistons and rings. So I'm going to write rings up here. And so the piston to ring seal, and then of course the camshaft, right? Those are the two things we're breaking in on that engine. Now the cam will break in within, you know, that first 15, 20 minutes of operation. The rings take a little bit longer. Those might take 500 miles, and that's about getting adequate cylinder pressures, forcing the rings into the cylinder walls to get those rings to break in properly. During that break-in period with the piston rings, we don't want oil that is too slippery, that's so slippery that the rings aren't going to break in properly, right? So again, the break-in oil gives you the extreme pressure lubricant you need for the cam to protect the cam, but it's not so slippery like synthetic oil would be that the rings won't break in, right? Now, what's the deal with synthetic oil? Well, it might be castor-based or something else, but typically a synthetic oil, 100% pure synthetic oil, it's going to be a man-made created base stock. And what does that mean? It means the base stock is going to be nice and uniform, and that every molecule is going to be really close to the same size. Well, what's the big deal about that? Well, in conventional oil, you're likely to have some of the molecules to be a lot bigger than others. You're also likely to have some of the molecules to be smaller than others. And then as you drive your car, the light stuff will burn off, the big stuff stays, and you just don't have the same uniform structure. And so you end up with an oil that's, you know, a conventional oil isn't going to be working the same over as wide of a temperature range. So that's where synthetic oil really shines. It's not necessarily the additive packages and stuff, although if the better the base stock, the less extra compensation or the less work the additives have to do. it's that with this uniform molecular structure, you have a oil that's going to be more stable over a wider temperature range. So with that, if you were to chill the oil down, you'll see that a synthetic oil is going to flow much more readily at low temperatures, even if it's still rated a 530 like the conventional was. They could have the same rating. You're going to have better thermal stability because of that base stock. So once the engine is good and broken in, it's not a bad idea to switch over to synthetic if you're looking to minimize engine wear, or you're going to be running your engine under extreme conditions. Maybe it's a truck and you're towing, or maybe it's a car, you're taking it out to the track or something. You're just running it hard. The synthetic oil is going to do better. The one thing I do see is people think, hey, I poured in synthetic, now I don't have to change it for 20,000 miles. I like to change the oil as quickly as it gets dirty. So remember that if the oil gets dirty by byproducts of combustion getting past the piston rings, if the oil's dirty, I want to get that oil out of there, okay? Not just discolored, because a lot of oils, as they get hot, they will naturally darken. But if the oil is truly dirty, you should get it out of there, and I don't care what the mileage is. So that might be 3,000 miles, it might be 3 track days, it could be 7,000 miles. All right. What about synthetic blends? Well, synthetic blends are all over the place currently because there's no standards. So you could have an oil that's conventional oil, 95% and 5% synthetic. Or it could be 50% conventional, 50% synthetic. All that stuff would be considered a blend, and that means they can put that blend label on the thing, on the bottle, right? So, I'm not a huge blends believer unless you know it's a good product and they have a good amount of synthetic in there. The idea is that you're getting some of the benefits of the synthetic without all the cost, right? Now, I was talking about some of the additives in engine oils. Here we have an oil that's a 5W20, so it's multi-viscosity, meaning that the oil will act as a 5-weight oil when it's cold, like a 5-weight oil would act, and a 20-weight oil when it's hot. Well, how do they do that? Well, they have these long molecular chains, and they call them polymers. So when the oil is cold, the oil molecular chain is kind of straight, and it flows easily. I think that's the 5-weight. When the oil gets hot, the molecular chain is supposed to kind of curl up, and that makes it more viscous. So think, okay, 20-weight. So that sounds really fancy, right? When you think, oh, these viscosity index improvers, or VIIs, molecular chains doing special stuff with temperature. When you see what it really is, which I just a year or so ago really got to see what it was, I was like, oh, that's not nearly as fancy as I thought. And I'd like to have an oil with less viscosity index improvers in it than more. Why is that? Well, what are viscosity index improvers? They're right here. If I can get this to play, let's see.
Those are synthetic. Treating it in the lab, treated versus extracted, and you're going to have uniform size. Everything's going to be the same size, right?
Okay, so what were you looking at there? That was, I was doing a lubrication training. I was working with a guy from Redline Oils, which those guys are right here in Benicia, right? Not too far out of the Vallejo area, so they're relatively local for us. And basically what you're looking at is a package of viscosity index improvers, but essentially all it is a bunch of ground up rubber. It's little tiny rubber bits that get ground up and fed into the oil. And the rubber, just like if you could take the bottoms of your sneakers, grind it up, throw it through the Miracle Vitamix blender, throw that in your oil, and that's what those viscosity index improvers are. That rubber content swells up and gets crazy when it gets hot, and tends to smooth out when it gets cold. And that's why a conventional oil over time if you really tested its viscosity, when the oil has been in the engine for 5,000, 7,000, 10,000 miles, it actually pours out thinner because that rubber content, the viscosity index improvers are all chewed up now. And that's why, like Sean Powers from Honda, he used to build their engines and then test them on the dyno. When Honda would do their horsepower ratings and stuff, they would always use used oil that was well broke in, because they'd have to run the oil that they would recommend, their factory Honda oil, whatever, right? And he said, well, we always made more power on used oil because it's getting chewed up and it's starting to thin out. All right, so choose the right oil for the job. And that depends on what you're gonna be doing. So we talked about the break-in oil already. So a big test of that is, well, what the heck is your job? If 95% of the time you're just driving on the highway, well, you don't need, anything more than stuff that meets your, original equipment manufacturer recommendations. But if you're going to be doing some track days where you might be logging 100 miles of track time on your car where you're at wide open throttle, well, maybe you want something that's like a full synthetic like that. If it's just a race car, well, maybe you want a race oil. So I've queued up this video here, and we're gonna watch what the guys from Redline have to say about it here. Boom. Okay, here we go.
Hi, I'm Cameron Evans from Redline Synthetic Oil, coming to you today from Camarillo, California at Timeless Customs. Today, we're going to talk about the difference between passenger car motor oils, the stuff you would run on the street, and Redline's racing oils, the stuff that you would run strictly on the track. The first of those differences is the detergency and the dispersants, the things that trap contamination in your motor oil as you drive around on the street for 2,000, 5,000, 10,000, if you're a Redline person, 15,000 miles. Very different from what you would see in a racing oil where you don't have those levels of detergency. Why? Well, after all, on the street, you're going to leave this oil in for a long time. In a race car or in a serious track car, you're maybe only going to go 2 or 3 weekends before you go to change the oil. The other big difference between the street oils and the race oils from Redline is the levels of ZDDP. Now, that's the anti-wear additive that you would know as zinc and phosphorus that protect hard, hot metal inside the engine when it's revved up. Cams, bearings, things like that. In the street car oils, we've got about 1,200 parts per million. That compares to API certified oils that are at a much lower level than Redline at 800 parts per million. Think about that. What you get typically at the auto parts store and what you order from Redline, you're getting almost 30% more protection just there. Now, the race oils, they've got 2,200 parts per million in that ZDDP package. That's way more than you'd ever need or want to run on the street. Now, what's the risk of that? Think about it. On the street, you've got emissions equipment, a catalytic converter. If you ever had any kind of breach of ring seal, or if the engine was starting to wear itself out, you could get oil past the rings. That oil might contaminate the catalytic converter. That happened with 2,200 parts per million. There's a chance you could clog the cat. So what are the situations that you might choose one of our street oils versus a race oil? Well, the obvious one is if it's your daily driver. That's going to be a street car oil all day long. But what if you're a guy that takes your car to track days? You can still run Redline's PCMO oil. Again, 1,200 parts per million of zinc, so there's more than enough protection. Both the race oil and the street oil are made from PAO and ester, right? So you've got the highest quality raw materials to protect you not only on your daily drive, but also when you go to the track. Any of you racers that are only taking a car to the racetrack, well, you're more than eligible to be using our race oil, and that's in drag racing, road racing, circle track, even 4-cycle go-karts. We get questions often about how often should I change my motor oil? And we're talking about for the street and for the track. So let's take your street considerations. So if you're the type of person who warms up your car in the morning, gets a cup of coffee, goes outside and commutes, let's say 40 or 50 miles to work, well, you're going to be eligible for a pretty long drain interval. If you're the type that starts the car, pulls it in gear, and only drives 5 minutes across town, chances are your motor oil never got up to temperature, and those dispersants and detergency really couldn't get activated. When it comes to the track, totally different story. We're not very opinionated on when people change out their oil at the racetrack. And that's not so much because we want to sell them more motor oil. It's more a matter of people are pretty opinionated about it. Let's touch on oil temperature and what you might experience at the track compared to what you would see on the street. Remember, motor oil, 212 degrees, that is where a 30 weight is a 30 weight. That's when it's that level of thickness. Take a drag racer, for example. He's going to go to the water box, do a burnout, and go stage. He may only get to 100 degrees of oil temperature. So he may select these straight weight products or things that operate a lot more like straight weights in 2 weight, 5 weight, 10 weight, very thin motor oils. So when you look at the front of the label on Redline's racing oils, you may see 30 weight race, 40 weight race. Remember, that does not mean that these oil are straight weights. Now, a lot of times you'll see other motor oil brands are coming up with 0.30s, 0.40s. They're dropping that oil weight. Well, there's sometimes a little bit of benefit from having that at cold start. One thing we like about Redline's race oils being more of a 1540 is getting up to temperature fast. Remember, the whole goal of the motor oil is to get it, all the raw materials up to working temperature so that they can do the job you're calling on them for. So let's collect a little bit of what we've learned today. The street oils and the race oils, they're made from similar raw materials, but really just at different levels. And they're very particular about when you should run them.
All right.
Hey, Mr. French, I've actually got to get ready and get going now, actually.
Yeah, we ended up taking a little bit longer than I thought. So let me wrap this thing up. So, and I understand I will record everything. Hey, there's a couple of tests online for you to finish this thing out.
Okay.
And then what I'm going to do is I'm going to set up your grade so that you guys will be able to see what your grade is on Canvas, and the grade will default to that unless we end up doing something where you come to like AR and do some extra work. But both you and Phil already have pretty darn good grades, so I don't think it'll be a problem. So, all right. So Phil, I'm gonna finish this thing really quick.
Guys have a good night.
Okay, you
Alrighty.
too.
Good night.
You too.
See you, Carlos.
See you, Phil.
All right, man. So my big thing on break-in, and I thought that was pretty good explanation about how it talked about like how important the temperature was to burn off the impurities in the oil, and I thought he did a good job with that. If we're breaking in our engine, it's a flat tappet cam. Do not let that engine idle down. You're relying on oil being thrown off the crankshaft to lubricate the camshaft, right? So you need a good amount of RPM, so there's lots of oil whipping around in there to move the impurities and stuff, like any little bits to wash those away and keep stuff lubricated. So fast idle break-in, during that break, so I'm going to say during that first 15, 20 minutes, right? Don't let it idle below 1500 RPM. Now for the first 500 miles or so where we're breaking in the piston rings, avoid high RPM. What does that mean? Well, maybe this engine would normally redline at like 7,000 or something. I wouldn't be going there. In fact, I would be staying below 5,000 RPM, because at higher RPM levels, the piston rings tend to flutter, and you can end up where you're messing up your brand new rings before they get a chance to break themselves in, right? So avoid high RPM on your engine. However, high amounts of load are okay, and a lot of times they'll want you to vary your speeds and loads. Piston ring manufacturers will say that. Well, why is that? They're basically trying to get you to put more load on there so that there's more combustion forces basically pushing the piston rings out against the cylinder walls. So high amounts of load are okay. I mean, I wouldn't be hitting the nitrous button or anything, but going up the Newcastle grade at 3,000 RPM, maybe trying to climb the grade a gear higher than normal. So you have a fair amount of load on the engine. That's okay. In fact, that load is going to help you break in and seat those rings a little bit faster. So high load is okay. You really don't want high RPM. And for the first 15, 20 minutes, as you're breaking in that camshaft, don't let her idle down. And if you do those things, you will, break in that engine really well and, set yourself up for a good engine lifespan. So that was my presentation on engine startup and break-in inside there. Phil, do you have any questions on that stuff?
No, that's pretty.
Okay. I probably killed you with too much stuff. So let me just do one more thing, because I at least want to get it in the video. Is I'm going to move my screen share back to our website. So there we go. There I am. So this is what I have put on the site for you guys to finish out this class. If we go to quizzes, so almost everybody had done the block work quiz. I have 2 other quizzes, and basically these 3 quizzes together were your final exam, and I had just chopped them up. So I have 10 questions here on let's see, this one's on engine assembly stuff like we've been talking about the last few weeks. The other one was on like engine balancing and crankshafts and pistons and stuff. So I had these quizzes for you to do. I am starting to load up your grades and stuff on there. I added one last discussion, but I need to fix. So this one actually is going to be like an extra credit one. You won't have to do that one, but it's like the second half of where they built the old school 6. I thought you had really good comments. You noticed right off the bat that they had not, they did their work in a different order. They didn't do the mains first. They were putting it in the cylinder sleeve and stuff, but with the equipment they had in that top, it was okay. So anyways, the second video in the series, they end up assembling the engine. So it follows some of the assembly we've been talking about and doing some pulls on the dyno, which is kind of cool. So that's there for extra credit for you. You got the quizzes on there, and I'll get your grades and stuff loaded up as soon as you guys get them done. I want to say next Friday is when everything's due, because the following weekend after Labor Day, I have to submit grades to Sierra College so they can get stuff done. And what's going to happen is that basically here I have this rush to submit it, but you're going to get a grade submitted, and it's going to be an incomplete for X amount of time until we either turn in the completed form, or it will default to whatever your grade is on the thing, which you're going to have a good grade anyways. But so that's how that's going to work. So you will get credit for it. All right. So with that,
Okay.
this is it. This is the last engine class of the semester. The last engine class for Sierra College, which seems really weird to me, but that's how it is right now. So if you get a chance, like earlier tonight, Carlos was saying he got a chance to go in and get his engine out of the engine lab. Please go and do that. If nothing else, just call up Ramon and or email him, and you should be able to get in there and get.
Yeah, I just talked to him today, so I'm gonna run there tomorrow morning and go pick it up.
Okay, good. I probably won't be there tomorrow, but I'll be in there next week. Be prepared. It's going to look pretty dismal in there.
I'm sure. It's so sad.
But when I was in there last week, all your stuff was still set right in its same spot.
Okay.
It's pretty good about making sure that people didn't mess with your engine parts. So, all right.
Perfect.
Take care. It's been a real pleasure having you in class. I hope to see you at AR in some future classes. And Jennifer and I really thought we would be having like a special barbecue for all the Sierra College students and graduates. we'll do something special next year at AR to recognize everybody who's coming in from Sierra. So with
Okay.
that, you take care of yourself. It really was super nice having you in class. Let me know if you have any problems with anything, and I appreciate you continuing to participate in the class throughout the semester. Okay?
Yeah. Thank you. I appreciate it. It's been
All right.
different but good. I know it's hard doing a hands-on class online.
Yeah, it's been a
You've
crazy
done well.
thing. I will
So
tell you that. Yeah, and we've probably done a better job with the balancing, like covering the theory of the balancing and the assembly than I normally get to do. So, anyways, thank you, Phil. You take care of yourself. Okay.
yeah, you too. We'll
All
see
right,
ya.
bye. We'll see you.
Bye.